We ran those experiments and they were super awesome, and we're going to talk about what their reactions were, what we saw, what was the sediment we created, what were the x-rays we saw, and what was the power we put in. So this is a very, very cool disclosure for you, which I think that a lot of people have kind of been waiting for. So here we go. So grab yourself a drink and let's get started. Deuterium-Oxide analysis of manuscript, take 1. Welcome to Quantum Kinetics. We have a very special episode for you tonight. What we're going to be talking about is our Deuterium-Oxide cold nuclear fusion transmutation manuscript that we did with the government, Department of Energy, PNNL, back in 2020 and 2022. This manuscript has not been published anywhere. We have tried very vigorously to try to get it published, but it was promptly rejected by many scientific edifices. And so you are going to get a special close encounter look at what cold nuclear fusion actually is supposed to look like using the Quantum Kinetic Fuser technology, which I'll show you. Here's the reactor. This is the Quantum Kinetic Fuser. We've shown this a few times in our, podcasts and all that stuff. So anyway, this experiment has a little bit of a history, actually. When we were doing our studies with PNNL, we were published for well water and ocean water with high acclaim for transmutation. And so the government folks and us decided, well, we have a little bit of money left over. Why don't we try doing another experiment? And they agreed, and we used deuterium-oxide. What this stuff is right here is extremely, extremely expensive water. This is laced with 99% deuterium heavy water. This comes from Cambridge Isotope Laboratories. And this stuff is very, very expensive. We bought about $5,000 worth of this stuff for the experiment. And so we ran those experiments and they were super awesome. And we're going to talk about what their reactions were, what we saw, what was the sediment we created, what were the x-rays we saw, and what was the power we put in. So this is a very, very cool disclosure for you, which I think that a lot of people have kind of been waiting for. So here we go. So grab yourself a drink and let's get started. So the manuscript title is called A Resonant Electrophysical Transmutation Method for Synthetic Nucleosynthesis. So for those who don't know, nucleosynthesis is basically the atomic binding process in stars. It happens in even in nebula sometimes too, where basically gravity pulls things together, causing them to fuse and then to become bigger and bigger and bigger and bigger. It's called nucleosynthesis. It's how nebula form. It's how planets form. It's basically how the universe forms in galaxies. So essentially we're saying here is a synthetic process for building universes. And the keywords for are cold fusion, transmutation, resonant circuits, super soft luminous X-rays, and nucleosynthesis. So I'll read the abstract to you. The abstract is, nucleosynthesis is a phenomenon that binds smaller atomic nuclei into larger atomic structures in high temperature celestial bodies. Current theories posit that it is impossible to overcome the Coulomb barrier repulsive forces to stimulate the fusion without extreme temperatures. Exploration of man-made nucleosynthesis primarily focus on heating matter to more than 100 million degrees until atoms begin to melt into a magnetically confined or physically compressed plasma field. While this approach releases energy and as nuclei fuse together, the energy input is immense. We're talking like millions of watts, right? Here in this study, we present a low energy input of 0.153 milliamps per square centimeter electrotransmutation process called ET. Method for synthetically stimulation of the synthetic nucleosynthesis using the patented Quantum Kinetic Fuser. When operated at a high purity deuterium-oxide matrix, basically dielectric, ET effectively fabricated unique nuclei elements with substantially lower power input than other cold fusion techniques. This includes just basic standard electrolysis. 24 hours experiment manufactured coagulated nanosediment with calcium, silicon, phosphorus, chromium, sulfur, magnesium, carbon, nickel, gold, manganese, titanium, aluminum, and even uranium components. The process also produced energy as indicated by the exotic Bremsstrahlung X-ray emissions. Previous ET experiments have shown the promise of this technology for applications such as radioactive water purification, and these new findings suggest that the ET or EPT process may be an energy-efficient means for making new elements. So that's the abstract of this. And we're going to go ahead and just, if you want to read the whole document, you can just go to our Patreon page, be a member, download it. It's copyright protected material, so just keep that in mind. Don't want to like show that around. It's just for you. And so we'll go ahead and go down to the images. We're just going to talk about the figures and the tables, just what we found and what we saw. Because if you want to read all the specifics, you can. It's kind of scientific, technical stuff. So we'll just kind of keep it as simple as possible for you. So let's jump into figure one. Figure one, what you're looking at here is the X-ray emissions of the experiments. So in this one, we did a 30 volt, 60 volt, and then a 90 volt experiment. And each one was for 24 hours. And in the top left, that's A, that's for the first minute. Those are the spectrums. B is for, was it 2 minutes? And then C, that one is for 12 hours. And then D is after 24 hours. So those are the emissions, X-ray emissions, through the process of this experiment. And if you look at it, the blue spectrum is for the 30 volts, the red is for 60 volts, and the 90 is the orange. And if you look at the green spectrum, that's a iron 55 radioactive sample calibration that we used. And you can kind of see that it's almost the same count rate as the experiment itself. So we know that this is definitely doing some type of beta decay, radiation or Bremsstrahlung electron slowing, which by the way, in gravitational flux fields like black holes, this is what you see. You see electrons slowing down, and Bremsstrahlung is electron braking. But electrons can also accelerate too and cause Bremsstrahlung. So that's something to be mindful of as well. So let's go a little closer into this. Now, when you look at this, you probably have no idea what you're looking at. But in most stars burn around, 5 million degrees to 11 million degrees, which is 1 keV X-ray. And if you look at these pictures, these emission spectrums, you can see that most of all, and by the way, black is all the spectrums combined. So when you see black, that's basically the main signature of this basically synthetic star. And there are no known stars to be over 200 million degrees, and the red, as you can see, has got the hump, and even the 30 volts, it was able to hit over 200 million degrees for 24 hours. Ladies and gentlemen, you're looking at the world record for nuclear fusion, sustained nuclear temperatures. We're talking 200 million degrees Celsius X-ray emissions from this reactor, continuously. So this is basically Nobel Prize stuff right here that you're looking at. And the academic edifice will not publish this. The only people that want to publish this are basically the foreign publishing agents like China and whatnot. They're the only ones contacting me wanting to get this paper. And, I just find it very funny that the American academic elite will not publish this. But here it is for you. So you can see that we definitely held nuclear fusion temperatures for 24 hours. We are basically the only company that can do that. So now we're going to go down to the next figure. Now what this is basically just histogram data of the experiment. So When you look at this, you can see that there's the 1B, which is a background radiation detection. That we do that between each session, just to make sure that there's no lingering radiation in the field or in the vicinity of the reactor. And you can see that it goes back to background. And the blue B2, you can see there, that is the calibration iron 55 sample. What I find very interesting about this histogram is that on the top one, that's 30 volts, that's A, B is 60 volts, and C is 90 volts. Check this out. This is indicative of star behavior, and I'll tell you why. Because colder stars burn longer. And the A, 30 volts, you can see that it burns hotter as time goes by. So at the lower power input, it wants to keep going. It has a self-generating emission spectrum. It wants to increase after 24 hours. From the beginning to 24, it starts ramping up, which is a very good sign that this is how nuclear stars actually operate. When you have a star that's burning too hot, too fast, it'll burn out. And you can see here in B with 60, you can see that it starts off nice and hot at 60, but then it tapers out after the 12-hour mark. And that is from all the sediment buildup from the magnesium, the iron, the chromium, the gold, the titanium, the uranium in there as well. So all the other elements that are going through nucleosynthesis are basically interacting or slowing down the burn rate of this synthetic star. And if we go to the 90 volt, you can see that, man, it starts off really hot and then dies down basically next to nothing. But it's still able to hold 200 million degrees after 24 hours. So just looking at this data, this tells you that this is doing a Mother Nature's approach to fusion, nucleosynthesis. And if you set the value, the gravitational flux field, low, she'll just keep going for millions of years. She'll just keep on going and doing her thing, which is exactly what we need for industry. We want low power units, low power reactors that you just set and you just leave them on and you have the pump running and they're just flowing water and they're processing at a very low power. We're talking like 1.9 watts. So this is really, really exciting that this technology is available for industry, and we're super excited to get it implemented into industry as soon as possible, running out of time. All right, so we'll go down to the emissions of the spikes. This is basically the raw data of the actual X-ray photon that the detector is detecting. This is an XRD CR100, something like that. I have to look it up again, but this X-ray detector is what they use for detecting black holes and nebula objects and whatnot. So these they look like interference, but they're actually not. What that is, if you look closely, what you're looking at there, that is called a compound nucleus event. Compound nucleus is when two atoms come together and then they quantum tunnel through each other and then they bind together. They start ringing. The nuclei interact with the wavelets interact as the nucleides form, and then they start ringing for a moment and then they ring out. That's just called compound nucleus. And you can see that these emissions are indicative of the compound nucleus that we see from our reactor and all the sediment buildup. So we're going to go down to figure 3 now, and we're going to get a little bit closer look at the sediment that was built up on the electrodes. So what you're looking at on the far left, on the bottom, you're looking at an SEM image or EDS image of what the sediment looked like on the electrodes. So you can see that the first row there, that's basically the source. The second row is 30 volts. The third row is 60 volts. And the last row D is 90 volts. Again, this is another indicative thing of stars. I love figure F. That is my favorite one, and I'll tell you why. Because if you squint your eyes and you look at that, what does it remind you of? To me, that reminds me of me looking up at the stars, seeing these scattered concentrations of just random Brownian concentrations of like fused star material. And you can see that forming on the electrode at low power, which to me, it feels like we're looking at an analog of an actual universe forming in this reactor. And because the magnetic field goes up when the voltage goes up, and the sediment buildup is greater as the voltage goes up, you can see that there's a massive caking going on the electrode here. And what I find very interesting is if you look at the 60 volt caking action and the 90 volt caking action, what do you notice? The one on the right, the D, has a massive, tight, bonded caking, and it's actually starting to turn black in certain spots, kind of like indicative of a black star or even a black hole. So what you're looking at here, for sure, in my opinion, and from the science and the astronomy knowledge I know, that this is definitely nuclear fusion, this is definitely cold nuclear fusion, and this is definitely nucleosynthesis. I'll tell you a little story before we go on about this sediment. We were transporting this sediment on a ferry, and we had everything in Ziploc bags. We had the reactor, we had the water, and we had the electrodes that were caked with sediment. When we were waiting in line at the ferry dock to get onto the ferry, a bomb guard dog came over to our truck and was sniffing the truck and was going crazy. Like, there were hundreds of cars at the ferry dock waiting. I think it was a Saturday morning. And it was insane. The dog almost scratched the door open. The dog was hitting its head underneath the car. It was going right for the cab where all the sediment and the reactors were. The dog was going crazy. And you can actually read it in our book too. It's got a really interesting story. You should check it out in the book. And when we rolled down the window, the lady was like, "Hey, my dog seems to really like your truck. Are you carrying any ammunition?" And I'm like, "No, I don't own a gun. I don't really like guns." And she's like, "Oh, well, I just want to, make sure my dog's doing the right thing. Do you have anything explosive in your vehicle?" And I was like, "No, I don't think I do." Okay, well, nice chatting with you. Well, turns out this is basically thermite. This is a thermo-explosive material that basically is what is used for stars. The dog was going crazy because it was sniffing out an explosive accelerant called magnetite thermite hydride material. So even the dog had an understanding of what was going on inside these reactors, which is, again, you should always trust your instruments. Always. Okay. We're moving on now to figure 4. Figure 4, this is what this is. After we did the electrodes and had them SEM checked, we scrubbed them with milli-Q water, which is basically really clean water. And so we scrubbed the electrodes into a vat of water, and this is the sediment that we collected using a magnet. So we used a magnet to move the sediment into a spot, and then we collected it with a filter. And what you're looking at is the dried sediment from the electrodes. And this is all of them. This is the 30, 60, and 90 all together, okay? And what you're looking at here is the SEM on the bottom left, E, and you're looking at basically just like a normal microscope on the top with a black light. What we see here is that these materials are very, very carbon-based, carbon-nitrogen-based, actually. And when this stuff is wet, you do not see the stringy stuff, all that stringy kind of neuron stuff. We don't see that when it's wet, but when it dries, that stuff shows up. Now, we've done research on this material, and there's a lot of stuff that we know about it that we're not going to tell you guys. But what I can tell you is that this material is very, very important for the future of humanity. And I'm not going to go into specifics, but this is super duper important stuff. And you can also see in the SEM that we also see some silver in there, right? So this is this material that's being made, this magnetic stuff, is really interesting. And I don't want to go too far into about what we know about this, but what we do know is that it is definitely biological. And I have more data. We have more data to show that as well as we go forward further. Okay. We're going to go to our first table, table 1, and what this is the cathode element concentration by weight of essentially the electrode itself. So this is, again, SEM EDS values of the electrode before it went into the bath, 30 volts, 60 volts, and 90 volts. And the big takeaway from this essentially is that we are indeed building carbon up on the electrodes, as you can see on the first line. There was already aluminum in the deuterium-oxide water from the processing that they do to actually enrich the deuterium, which is pretty standard. The one thing I really want to make note of here is the silicon. The silicon growth on the 60 was really quite stark, and also the magnesium was pretty stark as well. Now, the chromium going up is not that interesting because chromium has, stainless steel has chromium in it, but I find it very interesting that silicon went up, and I find that interesting, and you should too. Okay, so moving on to the next one. So this is the dissolved metal concentration that we got from basically the ICPs of the water itself. So these are the values of the source water, the treated water at 30, 60, 90. And what you can see here, ladies and gentlemen, is that this water went through a serious transmutation event. We grew barium, we grew calcium, we grew copper, magnesium, salt, lead, sulfur, palladium, vanadium, and I find this to be probably the most powerful information about this study. Because if you go down to the dissolved carbon and nitrogen concentration, you can see that the 60 or the 30 volt levels went up a lot. This is organic matter being formed in a synthetic reactor doing nucleosynthesis, CNO, nuclear burning at 1 keV, which is the same temperature as our stars. Okay. Ladies and gentlemen, this is proof that life itself is basically a safe nuclear event. That's what this means. We took basically water that you can't drink. It will make you sick. Deuterium-Oxide will make you sick. And we put it in this reactor, and it did a nuclear fusion temperature at low power, and it made organic carbon. And this is so interesting that it actually it's a full cycle. It's actually like a dissolved organic life-death cycle in the water. It's going through an actual, maybe even homeostasis event inside the water. And remember, if you saw in the other pictures, we had like the stringies that were, energized in a black light, and some of it wasn't. I'm wondering if that was the dead matter too. So this is really exciting stuff. Now you look at the pH level. The pH basically went to battery acid, basically stomach acid actually. So this reactor acts like a star. Way, and Mother Nature will give you everything that you need. Okay, I think that's actually all of it. There are supplemental images on the Patreon page, which you should totally check out. And you should become a member, because that will help the movement of cold nuclear fusion. So I really hope you enjoyed this session going over the manuscript that just cannot seem to get published in any academic edifice publishing. But again, thank you for tuning in to the resonant electrophysical transmutation method for synthetic nucleosynthesis. Again, truth is stranger than fiction. And remember, fusion is love, and love is fusion. You don't have to force it. It just happens. All right, we'll see you on the next one. Have a good rest of your evening. Take care.